All right, so welcome back, everyone. My name is Wilson, and today I'm here to take you through our AI system we have been developing called the title is Incentivizing Clean Air via low-cost sensor network with Spatio-Temporal Air Quality Monitoring in Uganda's informal spaces. This project focuses on addressing a very localized but serious health public issue which is air pollution in Uganda's informal food spaces. By this we mean chapati stalls, local restaurants, and any other informal spaces places in Uganda. And to monitor this exposure effectively and affordably, we use low-cost air quality sensors. So these sensors can detect pollutants like carbon dioxide, nitrogen dioxide, and particulate matter. And local restaurants operate in areas of limited resources like internet, power. So we use resource-constrained sensor networks, which are designed to run on low power, and they can also operate offline and later after they sync automatically when later connected to an internet connection. So therefore, once this data is collected, it is analyzed through spatial temporal pollution modeling, which helps us understand how air quality changes both over time and across different locations. And also venues that maintain good air quality throughout. They are given rewards, cleaner venues with badges, and also visibility boosts. So all this is done with an aim of cutting harmful air exposure and also improve the community respiratory health through cleaner cooking environment. And so before developing our system, we reviewed a number of case studies that have worked on low-cost air quality sensoring and monitoring frameworks. There are like 5 that we listed here. There is Kumar et 2018, whose study focused on low-cost PM 2.5, which is particulate matter, and carbon monoxide sensors using they were Arduino-based nodes. They achieved an accuracy of around plus or minus 15%, but their design was limited to a single pollutant type and relatively high power consumption. And the rest have been listed as shown above. So our problem statement was broken down into 2 interlinked problems, which is a domain application problem and the computational problem, right? So under the domain application problem, we have the higher exposure of smoke, carbon monoxide, nitrogen dioxide, and PM 2.5 in small eateries and chapati stalls. And we're talking about places where thousands of people spend their lunch, breakfast, or even supper at. There's also lack of affordable and continuous air quality monitoring in informal spaces. Right. Another problem is a limited awareness among vendors about harmful air quality and health risks. Then there is public health impact is under documented in these informal spaces. So many informal spaces are up to now they have no guidelines to follow. And then on the computational side, our main challenge is how to process noisy and irregular sensor data coming from multiple pollutant sources. We need to build a real-time spatial temporal models that can work even when the sensor coverage is sparse or very inconsistent. Also, another problem of being able to integrate the output into a behavior recommender and incentive system. So we have to ensure that each insight is actionable, and because our sensors operate in resource limited areas and settings, the entire system must be designed to run effectively and efficiently under with low internet or offline operations. And then next, our research was guided by both objectives and research questions to help fill the gaps addressed in the previous slide. And first was to determine the effectiveness of low-cost multi-pollutant sensor networks in informal spaces. And then next was to model spatial temporal patterns of air pollution and exposure in these small eateries. Then next was to design an incentive system that motivates the vendors to maintain cleaner air. So this was a system that gives rewards or badges and even shout outs, you can call them that, to the best or to the consistent food spaces with good air quality. And then the last was to evaluate the overall system performance under resource constraint deployment. And then the research questions were as follows. What patterns of air pollution exist in informal food spaces during peak meal times? Then what models can accurately quantify real-time exposure using low-cost multi-pollutant sensors. And then what features of this? Then what incentive mechanisms effectively encourage vendors to maintain cleaner air? So what are you going? So for the research contributions and outputs, first of all, we're on the verge of demonstrating a scalable, resource-constrained deployment framework, suitable for low power and offline operation, right? So this ensures that the system remains functional and operational, even in Uganda's informal spaces where resources like power and internet connections are unreliable. And we also deployed an neural policy layer that translates real-time air quality feedback into actionable recommendations and reward mechanisms. This is a clear representation of the system architecture of the AI system being built. And for starting from the sensor network layer, we deployed a couple of nodes, low-cost air quality nodes that can detect carbon dioxide, carbon monoxide, nitrogen dioxide, and PM 2.5 levels. So for the power, some of these are solar solar powered and some are battery powered. Then for connectivity, we're using Wi-Fi, which is 4G, which supports 4G, all LoRaWAN to ensure continuous data capture. So then next is a model and database layer. So this is where all the raw high frequency time series data from the sensors is streamed and stored, right? So the intelligence from the model and database layer is transferred to API and a service layer, right? Which is built in Python. All this is done through an API layer built with a fast API that provides a clean, secure, and scalable interface for all client applications. So all this information is fed into an interface that cleanly and easily describes our system. So our interface is divided into two. There's a public dashboard interface which can be a web service or a mobile application that is accessible to customers, and so where they can be able to view the air quality ratings of these restaurants before making their dining decisions. So even the owners of these stores, they have a dashboard where they can view their air quality in real time. They can view actionable recommendations on how to actually uh, restore their air quality. So we designed a number of models to represent our system, and first one is it's safe score model, and so it is a multi-layer perceptron, which is in short form an MLP for regression, specifically designed for its safe score prediction. So the architecture types are deep neural networks, DNNs, or multi-layer perceptions, which is MLP. It also includes a regression model for continuous value prediction and a tabular data processing with mixed feature types. So we incorporated a graph attention mechanism. This is because the air quality at one node or at one store, for example, in a restaurant is not independent. It is influenced by its spatial-temporal context. So what is happening in a nearby establishment and urban environment can greatly affect the air quality of a given store. The second model is the local temporal reasoning recommender model, and this model is about real-time interventions. And then its job is to provide the venue owners with actionable context-aware prompts at the precise moment when they are needed. So it integrates LSTMs, which is a long short-term memory for predicting that its F-score model. Then a contextual bandits, which is a decision-making layer, and then sharp for explainability. And the goal of the contextual bandit is to learn over time which intervention is most effective at maximizing the reward. In other words, which action is most effectively improves the air quality of a given situation. For example, uh, actions can be open windows, reduce the stove loads, and then sharp is mainly for explainability. So another model that we developed was the anomaly detection, which is which is basically to identify unusual pollution or sensor behavior across the spatial network of eateries. So we trained and evaluated using two major datasets, the air core dataset and then the data and Dalton datasets, which is an indoor air quality dataset. So the dataset was sourced from multiple publicly available air quality monitoring stations. Right? Its main focus is on PM 2.5 levels, which is a key health relevant pollutant. Its purpose in our study is to capture the spatial variability. And Dalton dataset was outsourced from Lamaka EL 2024 Git repository. So it geographically covers 30 Indo sites across rural, suburban, and urban regions of India. And its purpose is to capture real-world Indo pollution dynamics driven by cooking, ventilation. So next, we present the results and discussions for the anomaly detection model. This is the anomaly detection model, which is based on our temporal graph attention network architecture. The goal of this model was to automatically detect abnormal air quality events such as cooking spills, fires, chemical leaks, or even smoke from sensor streams. Starting with the bar chart on the left, we can observe the classification error rates per class, and then we also on the right hand side we also represent the loss and the accuracy curves, which show smooth and stable convergence across training, validation, and test sets. And then we also represent the confusion matrices for both validation and testing sets, which provide more granular insight into the data. And the heat map also highlights that the model strongly recognizes normal air quality conditions with very few false positives, which is critical for maintaining stability in real-time monitoring systems. And then moving on to the summary of our model results, one was a graph attention network whose task was anomaly detection, and it achieved an accuracy of 79% in identifying irregular patterns in the data. For PM 2.5 prediction, our graph convolution network achieved a mean absolute error of 10.46 and an R squared of 0.65. And our long short-term memory model, which is LSTMR, designed for forecasting basically, it achieved a slightly lower mean absolute error of 9.9 and an R squared of 0.67. And finally, the multi-layer perceptron, which is the MLP, that generates the itself score. This model achieved the best performance in our primary metrics. And then for the model selection and deployment, we opted to go with not just one specific model, but rather a combination of all the advantages. So we went for a combination of a couple of models. One was a temporal GAT, whose task is mainly for anomaly detection, as we discussed earlier. And the architecture is a graph attention, and the strength is detects events, right? So we took that, and then the second one was a Spatio-Temporal GCN, graph convolution network, and then an MLP, which predicts the itself score. It is a deep neural network, and its strength is it's easy to interpret. So on the demonstrating the developed product, we're working on an interface right now. SafeByte is the application name, SafeByte platform. So we have a view leader board where you can see the trending and the currently best air quality stores, and then we have restaurant dashboard, and then analytics. So this is kind of the first view into how the interface is supposed to look like, or is going to look like, but we have not yet really developed the 100% of the model. So this so going through the limitations that we faced during the process, number one is a limited sensor calibration accuracy. Number two is a spatial data in the informal areas, especially areas where network density is low. This creates spatial gaps in our spatial temporal models and slightly weakens the exposure interpolation. And then there was another limitation of power and connectivity issues. And then there was another issue of model drift over time. And another one was limited behavior data for incentives, for example. So without consistent user feedback, the recommender the recommender component cannot fully personalize the interventions. And then lastly was connectivity loss. So then we proposed a couple of improvements. Uh, First was integrating real-time calibration feedback using mobile reference sensors, which can dynamically correct the sensor drift. And then second is that we plan to deploy more low-cost nodes to improve spatial resolution in the areas. And then third was adopting hybrid solar systems with offline cache, which enhances power resilience and ensure continuous operations of the nodes. And then fourth, scheduling periodic retraining cycles with updated sensors and behavior data, which can mitigate model drift. So to conclude, the project has successfully demonstrated the feasibility of low-cost sensor networks for air quality monitoring, especially in informal food spaces. We have successfully designed and implemented the first behavior-linked incentive system targeting small-scale food vendors, and hence transforming air quality monitoring from a purely diagnostic process into an actionable behavior framework. We also showed potential for improving respiratory health through cleaner food spaces. And then for the future works, first we plan to expand our deployment to other urban centers beyond Kampala, and second to integrate wearable learning tracking for individuals. Also to explore federated learning for cross-city pollution predictions, and to strengthen the vendor incentive ecosystem through digital reward systems such as mobile badges, SMS alerts, and dynamic leaderboard ranking. And then the following our references used. You can take time and go through them if you want. So for acknowledgements, we extend our sincere appreciations to the Department of Computer Science, College of Computing and Information Sciences, COSIS, Makerere University, for their guidance and support. Special thanks to our supervisor, Mr. Galiwango Marvin, for his mentorship throughout this project. We also acknowledge AirCo and the creators of the Dalton dataset for providing valuable data resources. And finally, we thank our teammates, myself, Kaiza Wilson, Musinguzi Mark, and Rubankene Emmanuel for their collaboration and dedication to the success of the ITSAFE system. Thank you all.